Welcome to this problem walkthrough. Today, we'll explore problem number 472, titled Concatenated Words. This problem challenges us to identify words that can be formed by concatenating other words from a given list. It's a fascinating mix of string manipulation and dynamic programming. Let's dive in and break it down step by step. In this problem, we are tasked with finding all the concatenated words in a given list of strings, words. A concatenated word is defined as a string that can be fully constructed by combining at least two shorter words from the same list. For example, if the word catdog is in the list and it can be formed by combining cat and dog, then it qualifies as a concatenated word. The input to this problem is an array of strings, where each string consists of lowercase English letters. The constraints for the input specify that the list of words can contain between 1 and 10,000 elements, and each individual word can have a length between 1 and 30 characters. The output will be a list containing all the concatenated words from the input array. Let's explore some examples to better understand this definition. Consider the input array words equals cat, cats, dog, cat's dog, hippopotamuses, rat, cat, dig, cat. The output for this input will be cats, dog, cat's dog, rat, cat, dig, cat. Let's break it down. The word cats, dog, cats is a concatenated word because it can be formed by combining cats, dog, and cats from the list. Similarly, dog, cat's dog is another concatenated word as it can be formed by dog, cats, and dog. Finally, rat, cat, dig, cat qualifies as well, since it can be constructed using rat, cat, dog, and cat. However, the words cat, cats, dog, hippopotamuses, and rat are not concatenated words because they cannot be formed by combining at least two other words from the list. Let's look at another example to solidify this concept. In this example, the input is words equals cat, dog, catdog. The output here is catdog because the word catdog qualifies as a concatenated word. It can be formed by combining cat and dog from the list. On the other hand, cat and dog themselves are not concatenated words because they are not constructed from two or more other words in the list. This example demonstrates how the definition of a concatenated word relies on using at least two shorter words to form a larger one. Let's review one more example to ensure we fully grasp the problem. In the final example, the input is words equals apple, banana, orange. The output for this input is apple, banana. Here, the word apple, banana is a concatenated word because it can be formed by combining apple and banana from the list. However, apple, banana, and orange are not concatenated words because they cannot be formed by combining at least two other words from the array. As we wrap up the problem statement, it's important to note the constraints. The array can have up to 10,000 words, each word can be up to 30 characters long, and all words consist of lowercase English letters. Edge cases to consider include arrays with no concatenated words, arrays where all words are concatenated, or arrays containing duplicates or overlapping combinations. These details will guide us as we work towards solving the problem efficiently. To solve the problem of finding concatenated words, one approach we considered was the brute force method. The intuition here is to generate all possible concatenations of words from the input list and check if each word can be formed using other words in the list. This involves breaking the word into every possible combination of substrings and verifying if those substrings exist in the list. A key observation is that a concatenated word must consist of at least two smaller words, and we can use recursion or backtracking to try every possible way to split a word. However, this approach is highly inefficient. The process of generating all splits and validating them for every word results in exponential time complexity, which becomes computationally expensive and impractical for larger inputs. Due to this inefficiency, we decided not to pursue the brute force approach. Instead, we explored more optimized solutions, starting with a dynamic programming strategy. The dynamic programming approach builds on the idea of segmenting a word into smaller substrings and checking if those substrings exist in a hash set of valid words. By maintaining a DP array, we can keep track of whether specific prefixes of the word can be formed. For example, DP, I, indicates whether the substring from the start of the word to the ith position can be constructed using valid words. To ensure correctness, the current word being processed is excluded from the hash set. The steps include sorting the words by length, so shorter words are processed first, and using a hash set to store valid words as they are encountered. For each word, the DP table is updated to determine if it can be formed using the words added to the set so far. This method is more efficient than brute force, with a complexity of approximately n*k squared, where n is the number of words and k is the average word length. Despite its efficiency, we identified an even simpler alternative involving depth-first search and memoization that eliminates the need for a DP table. The depth-first search (DFS) approach with memoization offers an optimal solution by directly checking prefixes of a word and recursively validating the remaining portion. If a prefix exists in the hash set, the remainder of the word is checked recursively. Memoization plays a critical role here by storing results for substrings that have already been processed, thereby avoiding redundant calculations. Sorting the words by length ensures that only valid smaller words are used when constructing larger ones. The steps include sorting the words, maintaining a hash set for valid words, recursively checking prefixes for each word, and leveraging memoization to speed up the process. This approach is not only efficient but also intuitive, as it avoids the overhead of maintaining a DP table while achieving similar performance. By focusing on the recursive structure and reducing redundant work, this method strikes a good balance between simplicity and computational efficiency. The computational complexity of the DFS with memoization approach is similar to that of the dynamic programming solution. Sorting the words takes n log n, and for each word, recursive calls process at most k squared substrings. This results in an overall complexity of approximately n*k squared. We chose this strategy because it balances simplicity, efficiency, and ease of implementation. The recursive nature of DFS, combined with memoization, avoids redundant calculations and eliminates the need for additional bookkeeping like a DP table. Sorting the words ensures we only use valid smaller words to construct larger ones, streamlining the process further. While the dynamic programming approach is efficient, it introduces unnecessary complexity compared to the DFS solution. The brute force approach, on the other hand, is entirely impractical given its exponential time complexity. Overall, DFS with memoization provides the right combination of performance and simplicity, making it the optimal choice for solving this problem. To solve the problem of determining whether a word can be formed by concatenating other words from a given list, we can start by understanding the brute force approach. The first step is to iterate through each word in the list and check if it can be formed by concatenating other words, excluding the word itself. For each word, we generate all possible splits of the word into substrings. For example, if the word is cat dog, we generate splits like C plus a dog, CA plus dog, and cat plus dog. Once we have these splits, we verify if both the left and right substrings exist in the list of words. If they do, we know the word can be formed. This approach focuses on systematically breaking down the word and checking all possibilities. Now, building on the brute force approach, we also incorporate recursion to handle longer combinations. If a substring exists in the list, we recursively check whether the remaining portion of the word can be formed by other words. This ensures that we explore all possible combinations. Backtracking is used to backtrack from invalid paths and continue exploring other options. Finally, we return the result, true if the word can be formed using other words, and false otherwise. While this approach works, it's clear that it can become computationally expensive as the number of words or their lengths increase. The brute force method has significant limitations. Generating all substrings and combinations for every word leads to a computational explosion, especially with larger input sizes or longer words. The number of recursive calls grows exponentially in these cases, making the approach impractical. To address this, we can optimize the solution in two key ways. First, we use memoization or dynamic programming to store intermediate results and avoid redundant calculations. For example, if a specific substring has already been checked, we simply reuse the result instead of recomputing it. Second, we use a hash set to store the list of words, allowing us to check for the existence of substrings in constant time. These insights form the foundation for an optimized solution. Let's now look at the optimized approach using dynamic programming. First, we pre-process the data by storing all words in a hash set for fast lookups and temporarily removing the current word to prevent self-referencing. Next, we define a dynamic programming array, DP, where each entry DP I, indicates whether the substring from the beginning of the word to index I can be formed using other words in the list. We initialize dp0 to true, as the empty substring can always be formed. Then, for each endpoint I in the word, we check all potential start points j. If dp(j) is true and the substring between j and I exists in the hash set, we set dp(i) to true. At the end of this iteration, the value of dp(n) tells us whether the entire word can be formed. To make this clearer, let's walk through an example. Suppose the word list is cat, cats, dog, catdog, and we want to check if catdog can be formed. First, we add all words to a hash set for quick lookups, excluding catdog. The hash set becomes cat, cats, dog. Next, we initialize the dp array as dp equals true, false, 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 false. As we iterate through catdog, we find that at I equals 3, the substring cat exists in the hash set, so we set dp3 equals true. Later, at I equals 6, the substring dog exists, and since dp3 is already true, we set dp6 equals true. Thus, dp6 confirms that catdog can be formed by concatenating other words from the list. The optimized solution relies on two key data structures. First, a hash set is used to store the input word list, enabling O(1) time complexity for checking the existence of substrings. This ensures that lookups are extremely fast and efficient. Second, a dynamic programming array is used to track which substrings of the word can be formed. The dp array has a space complexity of O(n), where n is the length of the word being checked. Together, these data structures enable the algorithm to balance speed and memory usage effectively while solving the problem. To analyze the complexity of our solution, the brute force approach has a time complexity of O(n*2 to the power of n, where n is the length of the word. This is due to the exponential growth in substring generation. In contrast, the optimized dynamic programming approach has a time complexity of O(n²*m, where n is the length of the word and m is the number of words in the list. This is significantly more efficient. The space complexity for the brute force method is O(n) due to the recursion stack, whereas the optimized solution uses O(n) space for the dp array. When considering edge cases, we handle scenarios like an empty input list, words that cannot be formed, overlapping substrings, and very long words by leveraging the efficiency of dynamic programming and hash set lookups. The key operations in this algorithm include hash set lookups, dynamic programming updates, and recursive calls with memoization. Hash set lookups allow us to quickly check if a substring exists in constant time, which is critical for handling large numbers of words efficiently. The dynamic programming array is updated iteratively to track whether substrings can be formed, ensuring that we reuse previous results wherever possible. Finally, memoization minimizes redundant computations and recursive calls, making the algorithm scalable and efficient for larger inputs. These operations work seamlessly together to solve the problem effectively. Here, we begin by defining the find all concatenated words in ADICT method within the solution class. The first step is to sort the input list of words by their lengths. This is important because shorter words need to be processed first in order to build longer concatenated words efficiently. Next, we initialize an empty set called word_set to store the words we process along the way. This set will help us quickly check if a substring exists in the dictionary. Then, we define a helper function, is_concatenated, which determines whether a given word can be formed by concatenating other words from the word_set. Inside this function, we first handle the edge case where the word length is 0, returning false since an empty word cannot be concatenated. We then create a dynamic programming table, dp, where dp, I, is true if the prefix word, I, can be constructed from the words in our set. Initially, dp0 is set to true to signify that an empty prefix is always valid. The nested loops iterate over all possible substrings of the word, checking if any valid prefix exists in word_set and updating the dp table accordingly. Finally, the function returns the value of dp(n), where n is the length of the word, indicating whether the entire word can be concatenated. Now, we initialize an empty list called result to store the concatenated words that we discover. For each word in the sorted list, we call the is_concatenated function to determine if the word can be formed by combining other words from the word_set. If the function returns true, the word is added to the result list. Regardless of whether the word is concatenated or not, it is then added to word_set so that it can be used to form longer words in subsequent iterations. After processing all the words, we return the result list, which contains all the concatenated words found in the input. This approach ensures that we build concatenated words incrementally, leveraging the dynamic programming technique for efficient computation. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, find all concatenated words in ADICT, takes an array of words as input. The first step is to sort these words by their lengths using the arrays.sort method. Sorting ensures that as we process shorter words first, we can use them to build longer concatenated words. Next, we initialize a hash set called wordset to store already processed words, which will help us quickly check if a word or its substring exists. We also prepare a list called result to store the final concatenated words. The method then iterates through each word in the sorted array. For every word, we use a helper function, isConcatenated, to determine if it can be formed by combining two or more words from the set. If it can, we add the word to the result list. Regardless of the outcome, the current word is then added to wordset for future reference. This iterative design ensures efficiency and avoids redundant checks. The helper method isConcatenated implements the logic to verify if a word can be formed from other words in the set. First, it handles an edge case. If the word is empty, we immediately return false. Then, we initialize a dynamic programming array, dp, where dp, I, indicates whether the substring up to index I can be formed using the words in wordset. The base case, dp, 0, is set to true because an empty prefix is always valid. We then iterate through the word's length using two nested loops. The outer loop iterates over each character in the word, while the inner loop checks all possible substrings ending at that character. If a valid prefix is found, meaning dp, j, is true and the remaining substring exists in wordset, we mark dp, I, as true and break out of the inner loop. Finally, we return dp, n, which indicates whether the entire word can be constructed. This dynamic programming approach ensures we efficiently check each word, leveraging previously computed results to minimize redundant computation. We begin with the input list of words, cat, cats, dog, cat's dog. To make processing more efficient, we first sort the words by their lengths, resulting in cat, dog, cats, cat's dog. This ensures that we process shorter words before longer ones, which is critical for our approach. We also initialize an empty set called word_set to keep track of words we've confirmed, and an empty list called result to store the final concatenated words. Now, starting with the word cat, we call the helper function is_concatenated. The length of cat is 3, so we initialize a dynamic programming array dp of size 4, with dp, 0, set to true to indicate the empty prefix. Next, we check all substrings of cat. For each position, no substring matches any word in word_set, so the function returns false, meaning cat is not a concatenated word. Finally, we add cat to the word_set, which now contains cat. Next, we process the word dog. Similar to cat, we call the is_concatenated function and initialize a dp array of size 4. As we iterate through the substrings of dog, none of them match any word in word_set. Therefore, the function returns false, indicating that dog is not a concatenated word. We then add dog to word_set, which now contains cat, dog. Moving on to cats, the is_concatenated function is called again, and this time the dp array is of size 5. As we check its substrings, we find that the prefix cat is already in word_set, so we update dp, 3, to true. However, none of the remaining substrings lead to a valid concatenation, so the function returns false. Cats is added to word_set, updating it to cat, dog, cats. Now, we process the word cat's dog. We call is_concatenated and initialize a dp array of size 8. As we check its substrings, we first find that cat is in word_set, so we set dp, 3, to true. Then, we find cats is also in word_set, so dp, 4, is set to true. Finally, when we reach the end of the word, we discover that dog is in word_set, allowing us to set dp, 7, to true. This means catsdog can be formed by concatenating smaller words from word_set, so the function returns true. We then add catsdog to the result list, which now contains catsdog. At this point, we have completed processing all the words in this input, and the final output is catsdog. In the second example, we start with the input list of words, a, b, abc, abcd. After sorting by length, the list remains the same, a, b, abc, abcd. We initialize an empty word_set and an empty result list. Starting with the word a, we call is_concatenated. Since it is a single character, the function quickly determines that it cannot be formed by concatenation, so it returns false. We then add it to word_set, which now contains a. Similarly, for the word b, the function returns false since no substrings match any word in word_set. We add b to word_set, updating it to a, b. Next, we process the word ab. The is_concatenated function identifies that ab can be formed by concatenating a and b, both of which are in word_set. As a result, the function returns true, and we add ab to the result list, which now contains ab. We also add ab to word_set, updating it to a, b, ab. For the word abc, the function cannot find a valid concatenation, so it returns false. Similarly, for abcd, no valid concatenation is found, so the function returns false as well. At the end of this process, the final output is ab, representing the concatenated word from this input list. To understand the time complexity of this solution, we can break it into several components. First, we sort the list of words based on their lengths. This sorting step takes m*log m, where m represents the number of words in the input list. Next, we process each word to determine if it can be formed by concatenating other words. During this step, we use a helper function called is_concatenated. For a word of length n, we initialize a dynamic programming array, which requires n time. Once the DP array is initialized, we iterate through all possible substrings of the word to check if it can be formed using the other words. This involves a nested loop, where the outer loop runs up to n, contributing n, and the inner loop runs for each prefix of the substring, potentially adding another n per iteration. This means that the substring checks alone can take up to n squared time for a single word. The substring checks, therefore, contribute n squared for each word. To evaluate whether a substring exists in the hash set, we perform a lookup operation. On average, this operation is 1, but since we may perform up to n squared lookups per word, the total cost of these lookups will also be n squared for each word. After processing a word, we add it to the hash set to allow it to be used for subsequent checks. This addition operation is 1 on average and does not dominate the overall complexity. Combining all these components, the processing cost for one word is n squared, in the worst case. Now, let's consider the total time complexity. Suppose S is the sum of the lengths of all words in the input list. Since we process each word and each word requires n squared substring checks, the total time required for processing all words is s squared. Adding to this is the sorting step, which has a time complexity of m*log m. Therefore, the overall time complexity of the algorithm is the sum of these two terms, m*log m plus s squared. In terms of space complexity, the solution uses several components that contribute to the overall memory usage. First, there is the hash set, which stores all processed words. The space required for this is proportional to the total size of all words, which is OS, where S is the sum of the lengths of all the words. Next, for each word being processed, we allocate a dynamic programming array. This array has a size of n+1, where n is the length of the current word. In the worst case, the largest word length, n_max, will determine this contribution, making it n_max. Finally, the result list, which stores the concatenated words, could potentially include all the words in the input list. This would add another OS. Combining these factors, the total space complexity of the solution is S plus n_max. When comparing this optimized approach to a naive one, the differences in efficiency become clear. A naive solution would involve generating all possible concatenations of words and then checking if each word in the list matches one of these combinations. Due to the combinatorial nature of generating all concatenations, this approach has an exponential time complexity of O(2 to the power of m asterisk k, where m is the number of words and k is the average word length. Space complexity for the naive approach would also be exponential, O(2 to the power of m. By contrast, the optimized approach avoids this inefficiency by using dynamic programming and a hash set for efficient substring checks. The result is a dramatically improved time complexity of O(s squared, and a space complexity that is more reasonable, O(s plus n underscore max). Analyzing the best, average, and worst cases provides further insight into the algorithm's performance. In the best case, if all words are short and cannot be concatenated, the algorithm processes each word in O(n) time. The total time complexity in this scenario is O(m asterisk log m) plus s. On average, most words require O(n squared) substring checks, leading to a total complexity of O(m asterisk log m) plus s squared. In the worst case, when all words are long and most substrings require checks, the algorithm performs O(n squared) operations per word, resulting in the same total complexity of O(m asterisk log m) plus s squared. Mathematically, the dominant term in this complexity is O(s squared), which comes from the substring checks. Since the sorting step, O(m asterisk log m) is asymptotically smaller for large inputs, the overall time complexity simplifies to O(m asterisk log m) plus s squared. For space, the main contributors are the hash set and the dynamic programming array, leading to a final complexity of O(s plus n underscore max). When tackling the concatenated words problem, there are several common mistakes to watch out for. First, edge cases like empty strings or single-character words are often overlooked, but they can easily cause otherwise correct solutions to fail. Testing against these edge cases is a crucial step. Next, some solutions mistakenly check for substrings rather than ensuring that a word is formed by concatenating other complete words from the list. This subtle difference can lead to incorrect results if not handled properly. Inefficiencies can also arise from duplicate checks. Without memoization or caching, your solution might repeatedly compute the same word combinations, leading to unnecessary performance hits. Additionally, recursive solutions need careful attention. Incorrectly ordering the base cases and recursive calls can result in infinite loops or flawed outputs. Finally, brute force solutions, while tempting, often ignore time complexity. For large input sizes, such as when the word list exceeds 1,000 elements, analyzing and optimizing for performance becomes essential. Now, considering interview scenarios, there are key insights that can help you perform well. Recognizing patterns is fundamental. Problems like this often involve techniques such as backtracking, dynamic programming, or using data structures like tries. Identifying the right approach early can save valuable time. Scalability is another important factor. Interviewers frequently assess your ability to optimize for large inputs, so demonstrating the use of memoization or efficient dynamic programming approaches showcases your understanding of performance constraints. Explaining trade-offs also highlights your algorithmic design skills. If you discuss multiple approaches, like comparing brute force with dynamic programming, articulate the time and space trade-offs to show a balanced perspective. Lastly, always address edge case testing explicitly. Discuss scenarios such as empty strings, duplicate words, or cases where no valid concatenations exist. This proactive approach reflects a thorough understanding of the problem. It's helpful to connect this problem to related challenges to deepen your understanding. LeetCode 472, the concatenated words problem itself, is the core focus here. A great foundational problem to complement this is LeetCode 139, word break, where you determine if a string can be formed using words from a dictionary. Building on that is LeetCode 140, word break 2, which extends the word break concept to find all possible combinations. Another related problem is LeetCode 212, word search 2. While it focuses on finding words in a grid, it shares similar principles, like leveraging tries and backtracking. Exploring these problems can help you refine your skills and recognize recurring patterns across different challenges. Finally, let's discuss alternative approaches and their trade-offs. A brute force method generates all possible concatenations and checks if they form valid words. While straightforward, its exponential time complexity makes it impractical for larger inputs. A more efficient approach is dynamic programming, where you use a DP table to track whether substrings of a word can be formed using other words. This method avoids redundant computations and has a manageable time complexity of O, n asterisk m, where n is the number of words and m is the average length of the words. Another option is the tree data structure. By building a tree from the input list, you can efficiently search for valid concatenations, which is particularly useful when dealing with a large dictionary of words. Lastly, backtracking with memoization offers a balance between simplicity and efficiency. By recursively trying to form words and caching previously computed results, you can significantly reduce redundant calculations while maintaining clarity in your solution. Great job following along. To recap, we tackled the concatenated words problem and covered both naive and optimized approaches. Key takeaways include the importance of hash sets and dynamic programming for decomposition problems. Thanks for watching, and don't forget to like, subscribe, and stay tuned for the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!